Hello students, in this video we'll discuss an interesting property of Bessel's equation of order 1/2. So recall that Bessel's equation of order n Bessel's equation is the following form. It looks like x squared y double prime plus x y prime plus x squared minus a parameter nu squared y is equal to 0, right? We've studied this equation when nu is equal to 0 and when nu is equal to an integer n. In this case, what I'm going to do is I'm going to look at the case when nu is equal to 1/2 because it gives an interesting property that relates these Bessel functions to trigonometric functions. Let's consider the case, consider the nu equals 1/2 case. Nu equals 1/2. And then when we look at nu equals 1/2, our Bessel equation becomes x squared y double prime plus x, that's an x, y prime plus x squared minus 1/4 y is equal to 0. I haven't done anything much more fancy than just plug in nu equals 1/2. But now I'm going to put this into self-symmetric form, right? And so what I'm going to do is the following. I'm going to look for solutions of a product structure. So let's consider, and this is a classical idea when we're studying self-adjoint differential equations, let's consider solutions in the form y is equal to u times v, okay? And it becomes a little bit messy, but we're going to see we're able to put into a beautiful form really quickly. So if we do this, this is going to tell me that y prime, by Leibniz's rule, is going to be u v prime plus u prime v, right? It's good calculus practice. And then y double prime is our binomial Leibniz, right, which is going to be u v double prime plus 2 u prime v prime plus, I need a u double prime and a v, right? And you can sort of see the implicit structure when we do a second derivative over here. If I was to do a third derivative, it'd be u triple prime plus 3 u prime v double prime plus 3 u double prime v prime plus u triple prime v, and then I'm using those binomial coefficients to guide me in finding the higher order derivatives. Great. All right, so now what? Now we plug in, okay? So plug in. We can write this just as Bessel, I'll say this Bessel 1/2, the Bessel equation of order 1/2. And what will we have? We're going to have an x squared u v double prime plus 2 u prime v prime plus u double prime v, and then plus x times u v prime plus u prime v, great. And then x squared minus 1/4, and then u times v is equal to 0. Now we're going to gather the terms that are similar to each other. So what are the terms that are similar? Well, let's look at the v double prime terms. So we're going to have a what? We're going to have a u x squared v double prime. That's the only v double prime term, is this u x squared v double prime. Let's look at the v prime terms. What are the v prime terms? We'll have a 2x u prime. That's going to be a v prime term. And there's a v prime term over here. It's going to be a plus x times u. Those are my v prime terms. This term and this term are the only v prime terms. So I have an xu, and then I have a 2x. I have a 2x. So that's a 2x squared, actually. 2x squared u prime. Great. And then we have the u terms, right? What are the u terms going to be? The u terms are going to be, the u double prime terms, the v terms rather, excuse me, are going to be a u double prime x squared. That's a v term. And over here I'm going to have a plus x and then a u prime. That's a v term. And then the other v term is going to be an x squared minus 1/4. That's also a u term. And those are all times v is equal to 0. So I've taken the equation and made it much longer. But now the advantage is I can choose my parameter u to be whatever I wish. And so our objective now is I'm going to choose u such that this term over here is 0, right? So I'm going to choose u such that 2x squared u prime plus what? Plus xu is equal to 0. And from previous videos, remember this is called putting the equation into normal form, right? So this is called putting it into normal form. Put into normal form, which we've discussed in previous videos, right? For the normal form. Okay, so let's cancel on x, right? So this is going to say the same thing as saying that 2x u prime is equal to negative u. And that says that u prime over u is equal to negative 1/2 x. So if we integrate that, what are we going to conclude? We'll conclude that the log of u, of course that's the natural log, the log of u is equal to what? Is equal to negative 1/2 the log of x, which is the log of x to the 1/2 power, like that. So u is x to the 1/2, x to the negative 1/2. Good. And of course, we're going to need second derivatives, first derivatives and second derivatives of u. So what's the first derivative of u? That says that u prime is negative 1/2. Is negative 1/2 what? Is negative 1/2 x to the negative 3/2 power. And then u double prime is going to be what? Is going to be 3/4 positive, x to the negative 5/2. Good. So with this choice of u by construction, this term is equal to 0 over here, right? So now what we're going to do, that term is chosen to be 0. So now I'm going to divide by x squared. So what's the v equation going to look like? The v equation is going to be what? It's going to be v double prime, and then plus what? I have a x squared, and then u double, so it's going to be u double prime over u. That's going to be the first term, because I have to divide by x squared. Then I'll have a what? Then we'll have a, 1x cancels out, so we're going to have a plus u prime over ux, because there's x over there. And then finally, the u will cancel out over here, right? And we'll have a plus, the x squared divided by x squared is going to be a 1, and then a minus x squared over a quarter, minus 1/4 x squared. Applied to v is equal to 0. Now that equation looks really messy, but let's see what it simplifies to, right? This equation is going to simplify to what? V double prime plus u double prime over u is going to be what? So u double prime, so x to the negative 5/2 over x to the negative 1/2 is x to the negative 2. So this is going to be a 3/4 x to the negative 2 over here. U prime over u is going to be negative 1/2 x to the what? X to the negative 2. That's going to be a negative 1/2 x to the negative 2 plus 1, and then negative 1/4 x to the negative 2 applied to v is equal to 0. Okay, great. Now you should say, geez, it's still pretty messy, but look at this. This is 3/4, negative 1/2, and negative 1/4. All the x and negative 2's cancel out, and then we have v double prime plus v is equal to 0. I know how to solve this equation. It's a constant coefficient equation. So my v solution over here, v is going to be c1 cosine of x plus c2 sine of x, okay? So that's what v is going to be, and u I know to be root x. So my solution, j1/2 of x, is going to be x to the negative 1/2 power, and then what? And then times c1 cosine of x plus c2 sine of x, okay? Now, if I plug in x equals 0, I want j1/2 at 0 to be defined. j1/2 of 0 has to be defined, so j1/2 of 0 needs to be defined. Exists, and that forces c1 to be 0, right? So j1/2 of x is a constant c2, 1 over the square root of x, and then the sine of x. And now what I can do is I can actually write down what the solution to this equation is over here. So the solution of this of the j1/2 by the Taylor series problem is going to be the sum, k goes from 0 to infinity, of negative 1 to the k over k factorial, and then a what? And then a gamma of k plus 1/2 x to the power 2k, x over 2 to the power 2k plus 1/2, right? Is now it turns out that this thing over here, that gamma of k plus 1/2, is equal to what? We see this in the previous videos. We can actually find a formula for this. Is going to be the square root of pi, and then a 2k factorial over k factorial, and then 2 to the 2k, like that. Okay? And so what will happen over here is if we plug this in, what we're going to see is we're going to have a k factorial. We're going to have the k factorials are going to cancel. We have a root pi, and we have an extra factor of 2. So we can actually figure out by this formula what the formula for this c2 is going to be, right? It's going to involve a root pi, and then all of the 2's are going to cancel out except for an extra 1/2 on the top, right? So what this will be is this is going to be the square root of 2 over, I have a root pi in the denominator, so I have a root pi, I have an x square root in the denominator, and then I have the what? Then I have the sine of x. So we've just shown that j of 1/2 is the square root of 2 over pi x times the sine of x by appealing to this formula for the gamma function over here. Now it turns out we can use this formula over here that what can I say about the roots of j of 1/2? The roots of j of 1/2 are exactly on the positive axis are just the roots of sine. So I know that j1/2 has an infinite number of roots because it coincides with the roots of sine. So at pi, at 2 pi, all of those values are going to be equal to 0, right? And so in particular we see now that we have in particular 0 0 as well, because this has order 1/2 and sine has order 1 at the origin, right? And so I have a very beautiful closed form, and I've related now these Bessel functions of fractional order, half fractional orders, to periodic functions sine and cosine, right? And we'll see in further videos how we can look at all of the Bessel functions of order 1/2 or 3/2 or 5/2, and we can differentiate them over and over and over again to get recursion relationships. But now we've seen a particular example of a Bessel function, a remarkably beautiful example that relates Bessel functions to trigonometric functions. Thank you very much.